Greetings to all. This is Vaishnavi, Assistant Professor, IT Department from SNS College of Engineering. Now we are going to see about the parametric form for the curve. Parametric curves. Curves having the parametric form are called the parametric curves. The explicit and implicit curve representations can be used only when the function is known. In practice, the parametric curves are used. The two-dimensional parametric curves has the following form, that is P of t is equal to f of t comma g of t, or P of t is equal to x of t comma y of t. The functions f and g becomes the x comma y coordinates of any point on the curve, and the points are obtained when the parameter t is varied over the certain interval, that is a comma b, normally 0 comma 1. Next one, Bezier curves. Bezier curve is discovered by the French engineer Pierre Bezier. These curves can be generated under the control of the other points. Approximate tangents by using the control points are used to generate the curve. The Bezier curve can be represented mathematically as summation of k is equal to 0 of n pi bni of t, where bi is the set of points and bni of t represent the percentile polynomials, which are given by n of ni into 1 minus t into n minus I ti. Next one, Bezier curves, where n is the polynomial degree, I is the index, and t is the variable. Then the simplest Bezier curve is the straight line from the point P0 to P1. The quadratic Bezier curve is determined by the 3 control points. The cubic Bezier curve is determined by the 4 control points. Here the diagram represents the simple Bezier curve, that is P0 to P1, and then quadratic Bezier curve. It's and then next one is the cubic Bezier curve. Next one, B-spline curves. The Bezier curve produced by the Bernstein basis function has limited flexibility. First, the number of specified polygon vertices fix the order of the resulting polynomial which defines the curve. Second, the limiting characteristic is that the value of the blending function is non-zero for the parameter values over the entire curve. Then the B-spline basis contains the Bernstein basis as the special cases. The B-spline basis is a non-global. Next, here we have the B-spline curve diagram, that is U0 to U1, and then U1 to U2, and then that control points comes under the U2 to U3, and then U3 to U4. This dot represent the control point, and the dark black dot represent the not in the B-spline curves. Next one, B-spline curves. A B-spline curve is defined as a linear combination of the control points Pi and the B-spline basis function Ni. K of t given by C of t is equal to summation Ni is equal to 0 Pi Ni comma K of t, and n greater than or equal to k minus 1, and t belongs to tk minus 1 comma tn plus 1, where Pi is equal to, that is I is equal to 0, 1, 2 and up to n integer are the control points. Next, k is the order of the polynomial segments of the B-spline curve. Order k means that the curve is made up of the piecewise polynomial segments of the degree, that is k minus 1, and then ni comma k of t are the normalized B-spline blending functions. They are described by the order k and by the non-decreasing sequences of the real numbers, normally called as knot sequence. Ti, that is I is equal to 0, that up to n plus k. Here ni comma k functions are described as ni comma 1 of t is equal to 1 comma 0. Otherwise, if k is greater than 1, we have to follow the next formula. Next, here we have the comparison of Bezier curve and the B-spline curve. Bezier curve, they are not designed with the sharp blend, and the constant curve, they are designed with the sharp blend and the even corners. They are Bezier curves are less flexible. It is more flexible with the large number of control points. Here we have some of the comparisons. Thank you.